Elementary statistics practice test number 5 or module 5, which covers chapters 10, 11, and 12. We are covering chapter 11, goodness of fit and contingency tables. All right, we're going to look at goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13 at 0.05 significance level. Alpha is 0.05. Tester claimed that the 4 categories are all equally likely. Now, the steps that you see here, even if they don't write it, the question is really asking for it, because what is part A? State the null and alternative hypothesis. What is the expected frequency for each of the 4 categories? What is the value of test statistic, critical value, make a decision? All of those steps are the steps involved we need to use for the test of hypothesis. So a quick reminder, a goodness of fit is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Goodness of fit is always right tail test. Why is that? If the sum of these weighted square deviations, chi-squared is summation of O minus E quantity squared over E small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-square goodness of fit test is always right tail test. In other words, if we look at the formula, observed and expected value, either they are close or they are not. If they are close, then O minus E quantity squared becomes almost 0. In other words, this becomes extremely small, because remember, we're going to use the chi-squared distribution, which starts from 0 and goes to infinity, doesn't have a negative one. And so that's the reason we use it as a right tail test. Now, E is n over k, summation of observed values over k. If they are equally likely, that means they should happen with the same frequency or the same proportion, if you will. Add them up, divide by however many categories, in this case is 4, and we end up with 8, which means what? Here's the given. Multinomial experiment with k equals 4. Why k equals 4? There are 4 categories. Alpha, 0.05. We use a goodness of fit, and each expected frequency is supposed to be larger than 5. It is. And by the way, the reason is because if expected count is less than 5, the result of chi-square test won't be accurate. So let's go through the steps. As always, the first step is the null and alternative hypothesis. I am writing the formula for test statistic. Here I am writing the E, which we found it to be 8, the expected value for each case from the previous page. So we write H0, P sub 1 equals P sub 2, P sub 3, P sub 4. All 4 have the same proportion. And H1, at least one of them, you can write one of the proportions or probabilities. One of them at least is different. And this is a right tail test. By the way, when we say it's different, I want you to know it becomes a two-tail test, and some people may treat it as such. I will also show you the result for that. But generally speaking, we take the chi-square to be the right tail test. I mentioned that in case in some texts and in some courses, they stick with the two-tail test. The next one is calculation of test statistic. We have the formula. Let's plug in, and because we have only 4 pieces of data, it is fairly small and we can calculate it easily. We have the observed value, we calculated the expected, and we do the math, we end up with the following. So this is test statistic. Critical value comes from the choice of alpha. Degrees of freedom is n minus 1, or in this case, if we say categories, k minus 1. And As you can see from here, we are looking at the chi-squared. So chi-squared, what do we need? We need degrees of freedom, which is 3. And we need the area to the right, which is 0.05, and the answer is 7.815. Let's do the drawing. As you can see, this test statistic value is way into the non-rejection region. Take a look at this. Is the critical value. This is the test statistic. In a matter of comparison, non-rejection region, the decision is not to reject H0, fail to reject H0, don't reject H0, however you want to put that. So what does it mean? We go back to the first step to see what that means. If you are not rejecting H0, then the claim is not being rejected either. The claim becomes true, and then you do the writing. There is sufficient evidence to support the claim that the 4 categories are all equally likely. Now, if we were to do the two-tailed test, take a look at that. Alpha is 0.05. The area to the right would be half of that, 0.025. So that's one of them. That is chi-squared of the right. And remember, we need the area to the right to make a decision. This one is 1 minus 0.025, giving you this value. Therefore, for a two-tailed test, chi-squared of the left is this number, 0.216, and chi-squared of the right is this number. Again, take a look at the value of test statistic. If you were to graph it, is in between, fail to reject H0. However, as I've mentioned, things are a little bit complicated when it comes to this stuff, and normally the data is more than that. It is not done by hand. And if we use technology, what do we use? Again, this is one good and easy source to use online. That's the TI and chi-squared goodness of fit. You plug in, so we need L1 and L2. We put the command. Observed is L1, expected value is L2. They actually have already chosen that for you. Give it degrees of freedom, calculate, and here's the result. Take a look at the result. First, here's the chi-squared value that we got here. The thing we don't have here, and table actually doesn't do a good job on that, is the p-value. Take a look at the p-value. The p-value is larger than alpha. The p-value is 0.191, let's say. Larger than 0.05, therefore, fail to reject or do not reject H0. Let's quickly do another example similar to that. A professor asked 40 of his students to identify the tire they would select as a flat one, carrying 4 students who, this is a test. The following table summarizes the result. Use a 0.05 significance level to test the claim that all 4 tires have equal proportions of being claimed as flat. Now, this is the observed value. And again, the expected value, if they are equally likely, add them up, divide by size, or you would say the expected is that the proportion or probability is 1/4 or 0.25. So 0.25 that times the total number of observations. That's how you calculate that. So 2 ways, add them up, divide by 4, or you say 40 times 0.25 because you expect the 1/4 to be the proportion. So we see the expected values are larger than 5, therefore we can move on and do the chi-squared test. So H0 probability or proportion, if you will, or the percentage of the LF stands for left front, and then lowercase rf, right front, uppercase LR, left rear, and this one is right rear. So they are equal. You can even say they are equal to 0.25. And at least one of them is different, would be H1 or HA. The next step is to calculate the test statistic using the same formula we had. And since there are 4 categories, it's really not too bad, resulting in 4.6. As for the critical value, it was already done in the previous example, the same thing, 7.815. Let's look at the graph. Clearly, 4.6 is less than the critical value, way into the non-rejection. So don't reject H0, and the claim becomes true. There is sufficient evidence to support the claim that all four tires have equal proportions of being claimed as flat. And of course, the two-tailed test, the numbers happen to be the same as the previous one. This 4.6 is in between. If you were to graph that, again, for a two-tailed test, you end up with the same result. Test of independence using a zero point 0.05 significance level. Test the claim that when the Titanic sank, whether someone survived or died is independent of whether a person is a man, woman, boy, or girl. So the expected frequency has this formula, rho sum times column sum over the grand total. So let's see what we need to calculate. We need to calculate the sum in each column. We also need to calculate sum in each row. And this is the grand total. So total men, women, boys, girls, total number of survivors, total numbers who didn't. And so this number is the grand total. We are going to use this formula to calculate the expected value for each and every one of them. As you can see, it gets pretty complicated. So I'm going to show you the work for one of them. For this cell, the number is 332. So using this formula, we need the row sum. If you look at this row, the sum is 706. If you look at this, then times column sum. Look at this column, the sum is 1692. What is the denominator? This is the grand total, 537.360. What matters is to understand what that means, is the interpretation. And we can run this for each and every one of the cells, and we come up with the following result. Again, this is not done by hand normally, but we did one of them by hand. You can figure out the rest on your own. So what does it mean? Here's the explanation, and I want to go over. So if you look at this one, what does that mean? How many men survived? 332. This is the observed value. What is this value? This is the number of men that were supposed to survive if survivability and gender were independent. So if there was an independency, it would be more than 332, which is 537.36. As an example, what is the meaning of this number? Men who died, how many? 1,360. This is the observed value. This is actually what happened. However, if there was an independency, we would expect this number, which is much less than this number. And because of that discrepancy and the difference, then it gives rise to this calculation of a test statistic, which uses the chi-squared. Also, note that E in rows and columns are consistent, meaning if you add up these numbers, you get 706. If you add up these numbers, you either get 706 or you get a number extremely close. The reason I say you may not get an exact answer because of the round of error. Remember, we have decimals. If you go column-wise, the same thing, you get to the same answer. And that actually shows that your calculation is correct. So let's get a couple of things out of the way by looking at and recalling contingency table, or two-way frequency table is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize rows and the second one for columns. When data can be tabulated in table form in terms of frequencies, several types of hypotheses can be tested using the chi-squared. One of them is the test of independence of variable. In a test of independence of variable, we test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there is no dependency between the row variable and column variable. The test of independence of variable is used to determine whether two variables are independent of or related to each other when we have what? A single sample. Test of independence are always right tail test, and we use the sum of the weighted squares just as before, summation of observed value minus expected value squared over the expected value. And again, if the observed and expected values are close, this sum is small. So we have the same reasoning as before here. Here's an example test of independence using a 0.05 significance level. We want to test the claim that when Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl. So the requirements are the random selection, that is the assumption here. Results are frequency counts. Expected value, of course, as you remember, each and every one of them is way larger than 5. I want to discuss how you write the first step. You can just write it for this question, whether a person survived is independent of whether a person is a man, woman, boy, or girl, or just in general, the row variable is independent of the column variable. Now, for H1, you can just again write surviving the Titanic and being man, woman, boy, or girl is dependent, or in general, the row variable is dependent or related to column variable. So dependency or relationship means the same thing. So it's dependent or is related to. Therefore, let's calculate the test statistic using the formula, and degrees of freedom is row minus 1 times column minus 1, by the way. So you go through the process. If we look at the table that we had from the previous page put together, we plug in, we evaluate the test statistic, which becomes a very large value, 507.084. Critical value comes from the choice of alpha. Degrees of freedom is row minus 1 times column minus 1. 2 rows, 4 columns. So 2 minus 1 times 4 minus 1 is 3. And it results in chi-squared being 7.815. Now, I'm not going to worry about the p-value using the table too much, but just to give you an idea, this chi-squared value, remember the p-value would be the area, in this case, because the right tilt is to the right of this value. And this value is not in the table if you check the chi-squared table. The highest value in the table is 12.838, and the p-value becomes therefore smaller than 0.005. I wouldn't use a table by any means. If you do the graphing, you see that here's your critical value, and test statistic way into the rejection region. Remember, the area to the right of that would be the p-value. And because it's way into the rejection region, you are going to reject H0. Now, if you're rejecting H0, you go back to step 1. H0 means independent. So we are rejecting independency. That's really the bottom line. And that makes the claim to be false. So there's not sufficient evidence to support the claim when the Titanic sank. Whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. In other words, survival and gender are dependent. That's another way of putting it. As I mentioned, these things are done by technology. So you use the contingency table. You access the matrix as I put it here. In matrix A, which you choose it to be 2 by 4, you input the data. Then you do the test. You do the test of chi-squared. So chi-squared test. When you click on that, it automatically gives you observed value is A, expected value is B. Don't change that, just calculate. So notice what happens here. Number 1, if you look at this one, which is the B has been calculated, you just inputted A matrix only. It also calculates the B matrix. If you go pick up the B matrix, the one that we did the expected value, and it's difficult, cell by cell had to be done. We did one cell, they do all of them. Just look at the B matrix. What is the result of this test? Take a look. This is the same result as this one. Of course, they use more decimals. Also, take a look at the p-value. The p-value is 0. It's practically 0 because the test statistic is huge. So if you were to come up with the p-value, you say p-value is 0, and the decision is identical to the decision we made, which was rejecting H0. The next one is the test of homogeneity, which basically uses the same procedure using the following table with a 0.05 significance level. Test the effect of a pollster gender on survey responses by men. So the gender is different. So these are the men and women interviewers, men who agree, men who disagree. We want to see if it has an effect when we are being interviewed by different genders. So chi-square test of homogeneity. Recall, test of homogeneity of proportions is a test of the claim that different populations have the same proportions of some characteristics. The test of homogeneity of proportions is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. If you recall, the test of independence is for a single population. Now this is for different populations. Test of homogeneity is also right tail test for the same reason that we went over for the other two tests, the test of independence and goodness of it. All right, so again, we need to calculate the total. So going back quickly, so you need to calculate the total here. You need to calculate the total here. And as you can see, this is the grand total. We need to calculate the expected frequency for each cell using the same formula that we used previously. Cell by cell, it has to be calculated, and we end up with the following. Again, the meaning is very simple. For example, if you look at this cell, when men were interviewed by men, those who agreed, there were 560 that were observed. If they are independent, we would expect it to be a little bit more, 578.67. That's the idea behind it. Now, the requirements are met. We are looking at random selection. It's a frequency count, and the expected frequencies are 5 or larger. Let's do the test. And the very first step, we can write it in different formats. So let's go over the different formats we can write the first step. H0, the proportion of agree-disagree responses are the same for the subjects interviewed by men and subjects interviewed by women. P1 equals P2 equals P3, however many. Corresponding to that, H1 becomes the proportions are different. Or we could say survey responses by men are independent of pollster gender. That's really the same meaning, and that is the claim. Corresponding to this green line, survey responses by men depend on pollster gender. So that's the first step. The next one is test statistic. Let's calculate that. We go through the process. Again, this is normally done by technology. We don't have to worry about that. And the result is 6.529. Degrees of freedom, row minus 1 times column minus 1, 2 minus 1 times 2 minus 1 is 1. Alpha is 0.05. And critical value with degrees of 1, 0.05 from the chi-square table is 3.841. If we do the graph, test statistic is way into the rejection region, or the p-value is the area to the right of that. Therefore, we reject H0. So rejecting H0, go back to that. Rejecting H0 means rejecting independence, which is the claim. So reject independence. So the claim becomes false. There is not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. There is sufficient evidence to reject the claim of equal proportion. This is another way of writing it. Survey responses by men depend on pollster gender. I want you to look at the three different ways that I wrote here, because depending on the way they may expect you to answer, any of them is acceptable. If we were to do this with a two-tailed test, because remember, in essence, it is a two-tailed test, but we go with right-tailed test. Most everybody does, but if you come across any case that they don't, those are the values. And as you can see, this is way larger than the chi-squared of the right, and it gives us the same decision.